Okay, in this next example, we're going to take a look at heat flux in the thermal loads area. So what we want to do is go ahead and create a new study. We'll pick our steady state heat transfer option. And once the study is created, you also want to make sure you always have a property or a material property defined on your parts. And then what we're going to do is we're going to come up and we're going to apply a heat flux load. Now, this is a disc brake. And let's just consider a disc brake on a truck that's at the top of a hill, and as the guy drives down the hill a certain distance at a certain elevation, all this can be calculated out, he wants to maintain the truck speed at a certain low speed. That means he's going to have to hold his foot on that brake. So that's pretty much a constant. So what we're going to do is we're going to identify these two faces, and working out that calculation, we determined that we need to apply about a 1200 watt heat flux load, total load, to each side of this particular disc brake. Now, anytime that you apply a heat flux, and basically what a heat flux is it's a rate of energy that's transferred through a unit area, and in this case a face could be a curve, an edge, a point, or a feature, but in this case we identified two faces. Now when you're applying heat through heat flux, you have to be able to dissipate that heat in some fashion. And what we're going to use is a convection load, and we're simply going to apply a convection load to the entire model. Now, the one thing I want to do is I want to hold the shift key down and deselect the two faces where I got the heat flux load. It's obviously not going to dissipate there because that's where the heat is being applied. Now, when it comes to film coefficient, we'll talk about that a little later, but I'm going to set that at 22, and then I'm going to leave the ambient temperature at 20 degrees centigrade, which is about 68 degrees Fahrenheit. Now, obviously that gets a little bit messy looking, so you can turn off, especially you can turn off the convection load as it's applied to all those surfaces. And then I'm going to go ahead and kick off the meshing option. And also solve. And it takes about 30 seconds. So you'll watch it process through the mesh, then it starts to solve the heat transfer, and then it will process our results. Now when that's done, we'll get a temperature, and in this case we're working in degrees centigrade, and you can see it's at 375 degrees centigrade. Now just like in steady state, you can also do all of the neat things. We can, run an animation, see where this part heats up. We can also do a probe. So if we need to probe different points on this model to see exactly how hot it is, we can do that anywhere in the model, which is what you would expect. And we can see that our low temp is 170 and our high temp is 375. Again, which is about 708 degrees Fahrenheit. So what we want to do is we want to just drop that a little bit if we can, if possible. Not a lot of changes to make it drop it drastically, but we can make some changes to get the temp down just a little bit. One thing is to thin these out. They're way too thick. So what I'm going to do is I'm going to make a modeling change, and I'm going to take these down to 12 millimeters. I'm then going to move it up to, let's see, if I pick this face and move this to the corner, I can then rotate and maybe put a little bit of an angle face. I'm going to put minus 12. And then I want to change the thickness of this part. I want to maybe add a millimeter to each side. If I pick that first protrusion, you notice there's a dimension there. So if I grab that dimension, and one thing that's kind of cool in ST5 is we have this option to go to the left, go to the right, but we also have this option to do a symmetrical change. And I want to change this from 10.75 to 8.75, which should put a millimeter on each side. Makes it a little bit thicker, a little bit stronger. Now, again, we won't see a huge difference in heat change, but we will see a change. So I'm going to go ahead and resolve. So we've modified our model using synchronous technology. Very simple changes we should see a difference in our temperature, and hopefully it's down a little bit, maybe 15-20 degrees Fahrenheit. So it solves the heat transfer, processes the results, and here we should see our results come back a little bit better. And they have dropped a little bit. 361 is approximately 681 degrees Fahrenheit. So that's kind of a nice example of heat flux, applying a heat flux load to, in this case, two faces where the disc brakes get applied.